I need to start this one a little differently than usual, because I want to be straight with you before we go anywhere else. The headline you might see attached to a video like this one, something along the lines of scientists going quiet after Europa Clipper's first signal, has not actually happened. Not yet. Europa Clipper is still years away from even reaching Jupiter, let alone sending back data from Europa itself. What I want to walk you through instead is something a little different, and honestly, a little more interesting once you understand it properly. Not a fake breaking news moment, but a real, grounded look at exactly what is going to happen on a real fixed timeline when this spacecraft finally does arrive, and exactly what kind of signal could genuinely make scientists go quiet when it does. There's a reason it's worth taking the time to get this right, rather than just running with the exciting sounding headline. Space stories move fast online, and it is remarkably easy for a real, years away, mission milestone to get flattened into something that sounds like it already happened, especially once a video title gets clipped, reposted, and shared without any of the surrounding context. The actual Europa Clipper story doesn't need that kind of exaggeration to be worth your time. It is already one of the most ambitious planetary missions NASA has ever attempted, built around a genuinely serious scientific question, and it comes with a real, fixed countdown clock that anyone can check for themselves. By the end of this video, you'll know exactly where the mission stands today, what has to happen between now and 2030 for it to succeed, and precisely what kind of OF result would actually justify the dramatic reaction implied by a headline like this one. Let's start with where things actually stand right now. Europa Clipper launched from Kennedy Space Center on October 14th, 2024, riding a Falcon Heavy rocket into space as the largest interplanetary spacecraft NASA has ever built, with solar arrays that stretch out to roughly the length of a basketball court once fully deployed. A size dictated by just how faint sunlight becomes once you get all the way out to Jupiter's orbit, more than 5 times farther from the sun than Earth is. Getting a spacecraft this large off the ground at all required its own long, occasionally contentious engineering story. Congress originally mandated the mission launch aboard NASA's own Space Launch System rocket, a vehicle powerful enough to send it directly to Jupiter on a much shorter, roughly 3-year trajectory. When it became clear that rocket would not be reliably available on the mission's timeline, NASA shifted to a commercial Falcon Heavy launch instead, accepting a longer, more roundabout 6-year cruise using planetary gravity assists in exchange for a more dependable launch date and a substantially lower cost. Since launch, the spacecraft has been quietly working its way through that long, carefully choreographed cruise phase, using a gravity assist from Mars in March of 2025 to bend its trajectory, and it is now on course for a second gravity assist, this time from Earth itself in early December of 2026. That Earth flyby will fling it onward with enough additional speed to finally reach the outer solar system, arriving in orbit around Jupiter in April of 2030. Only after that, starting in 2031, will it begin the actual close flybys of Europa that the entire mission was built around. A planned sequence of nearly 50 individual passes, each one skimming past the icy moon, before ducking back out of Jupiter's punishing radiation belt to protect its instruments. So, right now, as of this recording, Europa Clipper is simply cruising. A spacecraft in transit, its instruments largely dormant or undergoing periodic checkouts, its true scientific mission still years away from beginning in earnest. That gap between launch and arrival is not a delay or setback. It is simply the physical reality of getting a spacecraft this size to a target this far away without the kind of enormous, expensive rocket that could have shortened the trip, a trade-off mission planners made deliberately, accepting a longer cruise in exchange for a more affordable, lower-risk launch vehicle. The mission's name itself is a small nod to that same spirit of a long, patient journey, borrowed from the clipper ships of the 19th century, vessels built and celebrated specifically for their speed and grace across vast ocean distances. A fitting name for a spacecraft asked to cross nearly 2 billion miles of empty space to reach its own destination. Understanding why this specific moon warranted building the largest planetary mission in NASA's history in the first place requires going back to a much earlier spacecraft, and further back still, to the first grainy photographs ever taken of Europa at all. Pioneer 10 and 11, and later Voyager 1 and 2, gave scientists their first real look at this small, icy moon during flybys in the 1970s, and even those early low-resolution images showed something odd, a surface almost entirely free of large impact craters, unusually smooth and bright, compared to the heavily battered moons nearby. For a solid body sitting in a solar system that has been getting pelted by comets and asteroids for billions of years, a crater-free surface is a strong hint that something is actively resurfacing it, smoothing over old scars the same way flowing water or shifting ice would on Earth. That early hint became a genuine scientific case between 1995 and 2003, when NASA's Galileo orbiter conducted an extended survey of the Jupiter system, and, in the process, gathered magnetic field readings and detailed surface imagery of Europa that reshaped how scientists thought about the moon entirely. Galileo's magnetometer detected a subtle, telltale signature in the way Europa's magnetic environment responded to Jupiter's own powerful magnetic field, a pattern best explained by the presence of a large, electrically conductive layer beneath the moon's icy surface, almost certainly a vast, salty, liquid water ocean. A conductive layer of solid rock alone could not reproduce the specific way that induced magnetic signal behaved as Europa moved through Jupiter's field, which is what let researchers narrow the explanation down specifically to a global layer of salty liquid water, rather than some other, less interesting subsurface material. Galileo's cameras added to that picture, revealing a surface crossed with cracks, ridges, and strange, jumbled terrain called chaos regions that looked remarkably like ice that had genuinely been floating, shifting, and refreezing over some kind of liquid layer underneath, rather than sitting atop solid rock all the way down. Some of these regions appeared almost like disrupted ice rafts, tilted and rotated relative to each other in ways that made far more sense if they had once floated freely on a liquid or slushy layer before refreezing into their current jumbled arrangement. Later observations from the Hubble Space Telescope added tentative evidence of water vapor plumes venting briefly from Europa's surface, hinting that material from that hidden ocean might, at least occasionally, be finding its way directly out into space where a passing spacecraft could sample it without ever having to drill through the ice at all. Put together, that evidence pointed to something remarkable. A moon of Jupiter, roughly the size of Earth's own moon, potentially hiding beneath its icy shell, and an ocean containing more than twice as much liquid water as every ocean on Earth combined. That single possibility, a genuine large-scale reservoir of liquid water sitting elsewhere in our own solar system, is precisely why an entire dedicated mission eventually got built to go back and look more closely. There's a reason, though, that this mission was designed around dozens of brief flybys rather than a single, simpler orbit settled directly around Europa itself. And that reason says a lot about just how hostile this particular corner of the solar system actually is. Jupiter's magnetic field is the strongest of any planet in our solar system, and it traps an enormous, punishing belt of charged particle radiation that surrounds Europa's orbit specifically, intense enough to degrade sensitive electronics and damage instruments over time if a spacecraft lingered there too long. Rather than risk parking Europa Clipper in a continuous orbit soaking in that radiation, mission engineers instead designed a long, looping orbit around Jupiter itself, with the spacecraft darting in for a single close pass of Europa every couple of weeks, before retreating back out to a safer distance to let its systems recover, repeating that pattern nearly 50 times over the course of the mission. It's a genuinely elegant piece of orbital engineering, trading a simpler mission design for one that keeps a multi-billion-dollar spacecraft alive and functioning long enough to actually gather the data it was built to collect. Europa Clipper carries 9 separate science instruments specifically designed to test different pieces of that hypothesis, and understanding what each one does is really the key to understanding what a genuinely significant first signal from this mission would actually look like. The centerpiece instrument, in many ways, is REASON, a dual-frequency ice-penetrating radar built to send radio waves directly into Europa's icy shell and listen for the distinct echo that would come back if those waves struck a genuine interface between solid ice and liquid water underneath, potentially all the way down to depths of 18 or so miles. A clean, well-defined artificial-looking return at some consistent depth beneath the surface would be about as close to a smoking gun for a subsurface ocean as ice-penetrating radar can realistically produce. Alongside REASON sits MASSPEX, a mass spectrometer designed to sample the extremely thin gas surrounding Europa and, crucially, any material venting directly out of possible plumes erupting from the moon's surface. If Europa really does occasionally vent geyser-like jets of water vapor from cracks in its ice, the way Galileo's data hinted it might, MASSPEX would be the instrument sniffing that vented material directly, checking its chemistry for exactly the kinds of compounds, organic molecules, specific salts, particular ratios of elements that would either strengthen or weaken the case for a genuinely habitable ocean underneath. A companion instrument called the Surface Dust Analyzer would examine solid material blasted off Europa's surface by tiny meteorite impacts, offering another independent way to sample the moon's chemistry without ever landing on it, essentially letting tiny natural impacts do the work. A drilling mission would otherwise have to do at enormous cost and risk. Rounding out the instrument suite, a magnetometer will take much closer, far more detailed magnetic field measurements than Galileo ever could, refining exactly how salty and how deep the hidden ocean actually is, paired with a plasma instrument designed to characterize the charged particle environment immediately around the spacecraft, as a way of double-checking those magnetic readings independently. A suite of cameras, including a wide-angle and narrow-angle imaging system, will map the moon's surface in far higher resolution than Galileo ever achieved. while a separate mapping spectrometer studies how different wavelengths of reflected light vary across the surface, a technique capable of picking out the specific chemical fingerprints of ices, salts, and other compounds mixed into Europa's frozen crust. An ultraviolet spectrograph will hunt specifically for the telltale signs of any active plume, watching for the characteristic glow given off by hydrogen and oxygen when water vapor breaks apart under sunlight, while a thermal imaging system scans the surface in infrared, hunting for warm spots that might mark active vents or recent geological activity, since a location leaking heat from below is exactly the kind of place scientists would want to examine most closely. So here, finally, is the honest answer to the question. This video's title is really asking, what would an actual genuine first signal from Europa Clipper look like? The kind dramatic enough to make an entire room of scientists go quiet. It almost certainly would not be a mysterious radio transmission or anything resembling a message. The realistic version of that moment is something quieter and in its own way. Far more significant, a reason radar return showing a sharp, consistent reflection at a specific depth beneath the ice, repeated across multiple flybys, that simply cannot be explained by anything except a genuine boundary between solid ice and liquid water. Radar data like that would not arrive as some single dramatic spike either. It would come back as a long, carefully processed profile, layer after layer of ice charted out beneath the surface, with researchers spending weeks or months afterward cross-checking that signal against instrument noise, against known ice properties, against every possible alternative explanation, before ever being willing to say publicly that they had found what they were looking for. Or the moment could look different still, mass specs catching a real, unambiguous plume in the act of venting, its chemistry showing organic compounds mixed with salts in proportions that immediately narrow down what kind of environment that ocean actually is. A result like that would likely unfold in a similarly unglamorous way at first, a spike in a mass spectrometer, a readout that a mission scientist notices during a routine data review, followed by weeks of careful analysis, confirming that spike represents genuine venting material rather than a contamination artifact or an instrument glitch, before it ever becomes a public announcement, let alone a headline. Either of those results, delivered as real, confirmed telemetry rather than a single ambiguous blip, would be the kind of moment that genuinely could leave planetary scientists briefly speechless, not because it proves life exists, but because it would represent the first direct physical confirmation of the exact conditions required for life to exist, sitting in a place nobody expected to find them when the solar system first began revealing its secrets to us centuries ago. It's worth being clear that even a landmark result like that would still only be the beginning of a much longer process, not a final verdict. Confirming the physical presence of a liquid water ocean, and confirming that ocean's chemistry looks broadly compatible with life as we understand it, are still several steps removed from confirming that life actually exists there. Scientists involved in the mission have been consistently careful about that distinction throughout the entire planning process, treating Europa Clipper explicitly as a habitability mission rather than a life detection mission, built to answer whether the necessary ingredients and conditions for life are present, not to search directly for organisms themselves. That distinction matters enormously for managing expectations, honestly, because the more dramatic, single-moment discovery many people picture when they imagine a mission like this is simply not what this particular spacecraft is built to deliver, even in its best possible outcome. This kind of careful, incremental approach is not new to planetary science, and it is worth remembering that Europa has occupied a special place in the search for life beyond Earth for decades now, well before this spacecraft was ever designed. Long before any mission was funded to look closely, planetary scientists had already identified Europa, alongside Saturn's icy moon Enceladus, as one of the two most promising candidates for a genuinely habitable environment anywhere else in our solar system, based purely on that early magnetic field evidence and the tantalizing hints from those early flyby images. That reputation only grew stronger as Galileo's data accumulated through the late 1990s, cementing Europa's status as a priority target long before Congress or NASA leadership ever committed the funding needed to actually build and launch a dedicated mission there. Multiple earlier concepts for a Europa-focused mission, including a full orbiter and even a proposed lander, were studied, redesigned, and in some cases canceled outright over the following decades as budgets and priorities shifted before the current multiple flyby design finally won approval as the most scientifically capable option that could realistically be built within cost and schedule constraints. What Europa Clipper represents in that sense is not a sudden new idea, but the culmination of a scientific case that has been quietly building, one careful measurement at a time, for the better part of 3 decades. What it can deliver, if everything goes according to plan, is something almost as remarkable in its own right, the most detailed direct evidence humanity has ever gathered that a second ocean, entirely separate from our own, genuinely exists elsewhere in our solar system, sitting quietly beneath miles of ice, orbiting a planet more than 400 million miles from the Sun, in conditions dark and cold enough that most of human history simply assumed nothing like a habitable environment could possibly exist there at all. That moment is still roughly 4 years away as of this recording, with the spacecraft's Earth flyby in December of 2026, marking the next major milestone on that long road, followed by years more of quiet cruising, before Jupiter orbital insertion in April of 2030, and the first genuine science flybys beginning the following year. There is no shortcut available to speed that timeline up, no clever engineering trick that lets a spacecraft this size reach the outer solar system any faster than the physics of orbital mechanics allows. Every step of that remaining journey, the Earth flyby, the long coast out past the orbit of Jupiter to reach aphelion in late 2029, the critical orbital insertion burn that will finally slow the spacecraft down enough for Jupiter's gravity to capture it, and the delicate Ganymede flyby planned to further shape its final orbit, has already been mapped out in detail by mission engineers years in advance, each maneuver timed to the day. What there is, instead of any shortcut, is a very real, very specific date already fixed years in advance, and a spacecraft already built, already tested, already successfully making its way through deep space right now, carrying instruments, purpose built to answer one of the most significant open questions in all of planetary science. That is a very different kind of story than a fabricated breaking news headline, but it is, I'd argue, the more genuinely exciting one. Because every year that passes between now and 2030 is not empty waiting time. It is the sound of a real, functioning spacecraft steadily closing the distance to one of the most promising places in our entire solar system to look for the conditions life actually requires. Ticking through each pre-planned milestone one by one, exactly on schedule, headed toward a moment that will not need any invented drama at all to matter. So no, Europa Clipper has not sent back a signal from Jupiter's moon yet, and nobody has gone quiet over any results, because there are no results yet to go quiet over. But the moment this video's title imagines is not fiction dressed up as fact. It's simply a real future event, already scheduled, already engineered, already years into its journey, waiting patiently at the far end of a very long and very carefully planned trip across the solar system. When that moment finally does arrive, it likely will not need any exaggeration at all to be one of the most significant discoveries in the history of planetary science. If you want to follow this story the honest way, tracking the real milestones as they actually happen rather than imagined ones, make sure you like this video and subscribe. Because between the Earth flyby later this year and Jupiter orbit insertion in 2030, there is a real, fully scheduled countdown already underway, and we'll be covering every genuine step of it as it unfolds.